Welcome back. My name is Jesse. I am a tutor in Melbourne and I also make GAMSAT videos as well. What we're going to do today is we're going to go through actually the final installment of the chemistry crash course series that I've been doing. I think this is video number 5 maybe, which is a little bit shorter than I expected. I guess I've done them as kind of long form videos for the most part. The early ones were kind of 50 minutes, an hour long or so. I've been trying to work them down so they're a little bit more bite-sized as well. But at the same time, I just wanted to make sure that all the content gets out quickly. I wasn't really just gonna drag it along in these short little 10-minute videos over the course of 6 months. But today's one should actually be really quite small because all we've got left is stereochemistry. And I'd originally planned to go through it in quite a bit more detail. But looking back through the ASA material again, there's really not much need to know a lot of the background theory for this. Again, all of organic chemistry is pretty much a visual game, and they're for the most part going to give you definitions of things anyway, even if it does come up in first year bio and chem. And they're doing that more and more because obviously they're going more towards the reasoning aspect. The likelihood of them asking anything beyond just a few points in stereochemistry is actually quite small. Looking at the practice material, they've very rarely strayed away from either chirality or chiral centers or enantiomers. And when they do, they give you pretty much full definitions and rules. They explain all the rules of how to determine a particular structural name and that kind of thing. So realistically, you should be able to go off of the instructions given. They do make them quite clear. So I think to keep the sentiments of this kind of free YouTube course true to what it was aiming to do, it was trying to get people up to speed with the background science, but it was also not designed to overwhelm people and make people think that it was a content exam. And so I think that keeping it short is actually going to be the better way to approach this. If people do have questions about specific things, I'm more than happy to answer them. But I think making a full video on it would actually kind of detract or confuse people as to what to expect in the exam. We want this series to give people a really strong understanding of exactly what will come up. So pretty much what we're going to go through is just what is stereochemistry quite quickly. We're also going to make a review of isomers, including non-stereoisomers as well, and comparing them. And then we'll be looking at chiral centers and chirality, and then also how to test for enantiomer structures or enantiomer pairs as well. So all of the diastereomers, meso compounds, and that kind of thing, conformational isomers, these I'm going to actually leave off because looking at the content, they barely ask about them ever. And if they do, they pretty much explain how to determine if something is one of those isomers. So they're really not relying on pre-existing knowledge there. So the first thing is just in terms of what is stereochemistry. So we've looked at different aspects or different kind of divisions of chemistry. So you've got inorganic chemistry, which is looking at metals, and then your kind of benchtop chemistry, acids, bases, that kind of thing. Then you've got organic chemistry, which is everything that is carbon-based. So looking at hydrocarbons and their derivatives and the different reactions that can produce or synthesize these compounds. And then also being able to name them, identify their structures and their functional groups, and attribute that to features. Stereochemistry is kind of a subdivision of organic chemistry, where technically we're still looking at organic compounds, but now we're looking at a specific type of isomer, i.e. alternative structure of a compound that has the same ingredients or the same building blocks, i.e. the same number of each atom or element, but arranged in a very specific way. So that obviously then brings up what is an isomer. So isomers, it kind of comes from the name, iso meaning same, and then mer meaning part, so same parts. And it really just means that you've got all the same ingredients, so but it's just going to be rearranged or reorganized on the actual structure itself. And therefore you technically have different compounds, different names, different features, different characteristics, but it's not in the exact same structural arrangement as another, right? So it's effectively like a shuffling of the ingredients. But then we can break down isomers a whole lot further. So we can break them down into structural or constitutional isomers. And then we've got the other half, which is the stereoisomers, which is what we're going to focus on. So let's dive right into it. So here what I've done is I'll reference this as well. I'll leave a link underneath. So if people want to go and actually have a look at this image for themselves, this is probably the best flowchart, saves me having to write it all up. Best flowchart that kind of summarizes exactly all the different isomers to be aware of, but we're really not going to need all of them for GAMSAT. So on the left here, you can see it's phrased by a bunch of questions, which I think is really helpful. Do the compounds have the atoms connected in the same order? No. So if the atoms are all there, but they're arranged in a different order, so they're connected to different things, then it makes a constitutional isomer, which is not a stereoisomer. We'll come to the stereoisomers in a moment. And so really quickly, there's 3 then different types. The likelihood of you needing to know these names, next to none. I wouldn't really bother with it, but they do have very literal names. So functional isomers are those that have the same ingredients, but they use those ingredients to make different functional groups. So you can see here, this one has an alcohol group, whereas this one here has an ether link instead. But if you count up all the carbons, hydrogens, and oxygens, they will have exactly the same number. So they've got the same ingredients, but they're arranged in a different structure, right? Using different functional groups. Then positional is that you've got the same functional groups, but the positions of those pieces are in a different arrangement. So you can see we've effectively moved the hydroxyl group or alcohol group over to the second carbon rather than the end carbon. So these 2 here would have different names. This here would be propanol, and this here would be 2-propanol or propan-2-ol. It's probably better, propan-2-ol. So very, very similar, but they do have different features. We can see the first was a primary alcohol, the second is a secondary alcohol. And we saw in the previous crash course video that if you were to say oxidize those alcohols, you would actually get different products. The first one would give you an aldehyde and then a carboxylic acid, whilst the second would give you a ketone. So we have to acknowledge that they are different compounds, but they're using the same ingredients. And then finally, skeletal is where you're actually shuffling the carbon arrangements. So instead of having here, we've got butane, we've taken the methyl group here and then just jumped it onto technically the second carbon here. And that's it. So these are all of our structural or constitutional isomers. We're not really going to look at that much today. So stereoisomers, that's where they're actually still arranged in the exact same way. So there's no changes to the carbon chain or the attachments to the carbon chain. That makes it a stereoisomer instead, if it is going to be one of them. But then it comes down to the actual 3-dimensional arrangement of those attachments to that main carbon chain. That then can create differences as well. So here we care more about the configurational side, and then following down, we want to follow this way and look at enantiomers. So again, yes, there's all these other details for all the others. I can quickly go through them. So with stereoisomers, if the compounds can be interconverted by rotation about single bonds, then we have conformational. So you can see effectively we're just taking, like say, this loop here on this 6-membered ring, and then we're swinging it down, right, to form this shape here. So we have the kind of boat and chair conformations is what they're usually referred to as. Here we have an example where we have a methyl group sticking straight up, so vertically, or we could have it arranged where the hydrogen would have been and have it sticking out equatorially, right, or flat horizontally, and that's what that one forms. So these are examples of conformational isomers because they have rotations about a bond of their attachments, and that then can create different compounds as well, even though the attachments are all the same. So if I just get rid of that for a moment, we have configurational isomers, so they don't have any of that rotation, but instead it could be you get isomerism because of restriction to rotation. So we get that in double bonds, and you can get this cis-trans isomerism, where we have trans is where you have the bonds either side of the double bond pointing in opposite directions, whereas cis is where they're moving in the same or directed in the same direction. This would be cis. And we can also see it in something like a cyclohexane. We can use this wedge and dashed line notation. Wedges like this, solid wedges, they mean that the bond is kind of directed out of the page at an angle at us, and the dashed one is into the page away from us. So this would be trans, because you can see one's out, one's in. Here they're both out, so that would be cis. And you can also have both in as well. That would also be cis. It would be the same compound though. It would just be spun around. We'd be looking at the back side of it. If there's no restriction to rotation, then you have optical isomers. The only reason they're called optical isomers is because they do have interaction with light. We don't need to worry about that for GAMSAT at all, so we're just going to leave that out. There are 2 types, diastereomers and enantiomers, and like I said, we're really just going to look at enantiomers. So the test comes down to whether or not the object or the compound has a mirror image that is not superimposable with its original, right? So a non-superimposable mirror image. And the way that we actually test for that, there's 3 steps that we follow, right? So number 1 is you draw the mirror image. And we'll do this in a moment. Number 2 is then you rotate the original, not the mirror image, but you rotate the original by 180 degrees. And then you superimpose them. And the reason why we do that is because when you do a mirror image, you do get a flipping super image. Superimposable, I can't talk and write at the same time. Superimposable. The reason why is because the rotation of the 180 is in the mirror, you're going to get a flipping of everything. So if you rotate the original, you haven't actually changed the compound. You're just rotating it to see if it ends up in the same arrangement as the mirror image. If it's a different arrangement, then it means you have enantiomers. If it's the same arrangement, it means you do not have enantiomers. If we do that, we can take this example here, right? And I'll just redraw it. So we've got a carbon in the middle. We'll do a little bit more detail. We've got an ethyl group, which is pointing straight up. We've then got a chlorine group, which is flat in the axis to the side. And then we have a methyl group, which is coming out of the page at us. And then we have a hydrogen that's kind of going slightly into the page on the right. So if I were to put a mirror here, like this, just to pretend like that's straighter than it really is, and then we would reflect it, right? So we know that it would only reflect things in this axis. So that would mean that the hydrogen would now be on the left, but it would still be into the page. So we would have our hydrogen like this. We would have our methyl group still out of the page, like this. And then our chlorine would now be fixed, pointing the other way. And this, because it's actually parallel to the mirror, we won't see any difference at all, right? I mean, if I do it in full, I'll do it backwards entirely. So it'd be C, H2, C, H3, right? It doesn't really matter all that much though. So now we've got our mirror image. So then the second thing that we do, and I'll do this maybe in another color, is we're going to rotate this one by 180 degrees, right? In that same plane. So what we're going to get there, I'll just do it underneath, is we'll see that methyl group still won't change, right? That'll still be sitting at the top because that's just spinning around on its axis. However, the chlorine, I like to do this one first, that'll now flip to the other side, but it'll still be in the plane of the page. But since the hydrogen was into the page, it'll do a 180 and now come out of the page. So we will now see the hydrogen getting the solid wedge, and likewise the methyl group will now be into the page. Like this. And if we now compare these, if we were to try and superimpose them, and here's what I can do. I can just, get everything, there we go. If I now try to superimpose this, you'll see that it hasn't matched up. We've got hydrogen with methyl coming out of the page, and then we've got methyl and hydrogen into the page. So they're not matching properly. Everything else is matching, but we don't have a complete match over here. That would mean that the image, the mirror image, is not superimposable with the original. Because remember, the pink one, 180 degrees, rotated, is still the original. It's just spun around to try and match it. And so what that would mean is that they would be enantiomers. I'll just get rid of all of that now, because we don't really need the pink one, because it's the same as the original. That would mean that these two here, these are enantiomers of one another. And it means that the original has an enantiomer, that is its mirror image, like that. Cool, and that comes down to that 3-dimensional arrangement in space of its 4 attachments, right? Now what I have done is kind of jumped over something to avoid it for the moment. The only way that you could ever possibly have an enantiomer, it's not a guarantee for an enantiomer, but it's a requirement, is you need to have a chiral carbon. So chirality, right? Normally this is taught at the start, I'm going to do this second. Chirality is, it's often referred to as like handedness. So the idea that like our left and right hands are mirror images of each other, right? But are not superimposable, because if I rotate this one by 180 and then try to overlap it like this, it looks like they're overlapping, but I'm actually got the palm side and the back side facing you. So these two hands are actually not the same in that way, right? They're almost the same, but remember, it's also about the orientation of everything as well. So technically our hands have chirality, but really in chemical compounds, we're referring to a specific carbon having chirality, right? And so chiral carbons are carbons that have 4 completely unique attachments. That's all you need. If they have that, then they must be chiral. It doesn't immediately mean that you have enantiomers. Not all chiral carbons or not all chiral compounds have enantiomer pairs, but this would be the test for it that we've just done. But in terms of just chiral centers or chiral carbons, same thing. You just have to have 4 uniquely different attachments. So here we can see that all 4 attachments, 1, 2, 3, 4, they're all uniquely different from one another, making this a chiral carbon, which we often do little asterisks on them. So if you ever see that, it means that it's a chiral carbon. Whereas if we look at the methyl group, that is not a chiral carbon, because although it's attached to all of the other stuff, I'll just kind of scribble CH2, CH3, H. If we focus on this methyl group here, this is one of its attachments, this whole lump, but then it's got 3 other attachments, but they're all the same as each other. So we don't have 4 unique, so therefore that carbon would not be chiral, right? And therefore does not have the opportunity for handedness or enantiomerism. If we jump back up, I've got here just as an example, because this is the kind of thing that they would do. They might ask you to count the number of chiral carbons in a compound. So this is the structure of ascorbic acid or vitamin C. And all we have to do is just look at all of your carbon corners, right? So here, 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 and then all the way around the ring, like that. Not the X is obviously an oxygen. And all we have to do is, the first thing is, if there's any double bonds, there's no way it can be chiral because double bonded carbons only have 3 attachments because of that double bond taking up 2 spots. So therefore you immediately can't have chirality. So already this one can't be chiral, this one can't be chiral, this one can't be chiral. These 3, however, have a possibility. So if we look at this one here, because it has to have 4 attachments with the skeletal structures, remember they don't draw in hydrogen, it would have to have a hydrogen here and a hydrogen here. Because it's got 2 identical attachments, it does not have 4 unique ones, and so therefore this is also not chiral. If we look at this one, however, we can see there would be a hydrogen, that's different. Then we've got a hydroxyl or an alcohol group, that's different again. Looking this way, we have both a CH2 and an OH. So we take into account everything that is actually attached. So think of standing on that middle central carbon, looking in all 4 directions and thinking, do I have a different view in all 4 directions? If you have a different view in all 4 directions, you have chirality. So then we look to the 4th one, and this is absolutely a different view to everything else. So therefore we have 4 completely different attachments. And so that would be a chiral center in the compound. So we'll put a little asterisk on that. We look at this one. So we've got hydrogen, then we've got, looking this way, we see an oxygen. Looking this way, we see a carbon with hydroxyl attached. So even though it's both attached to the exact same structure, it has different views. It has different perspectives. That's why I use that trick of standing on the carbon, right? And then finally, the 4th is this whole kind of chunk here, which is different again. So that has 4 different attachments as well, and so that would also be chiral. So vitamin C then has 2 chiral centers, just like that, right? And that's really the skill that they're going to assess, right? They're going to ask you how many chiral centers does it have? Or it might say which, how many of the structures given. They might give you a big list of structures and say which of them are chiral or how many of them are chiral. So long as there's at least 1 chiral carbon, it's a chiral compound. Otherwise, it's referred to as achiral. And then finally, what I thought we'd do as well is just jump across. There's this tool here that I found. It's called moleview.org, and it's a free kind of simulator where you can pretty much search or draw any compound, and it'll give you a 3-dimensional picture of it. So if you have one of those plastic chemistry sets, those are really helpful for this stuff. But if you don't, then you can always just use this as well and play around with it. So I've got here just methane, and you can actually click and drag. I'll link this underneath as well so people can find it and kind of play around with it. So if we look at this here, we can get a better sense of what we were drawing before, right? So the idea is that we would spin it so that this hydrogen here, this is pointing flat in the plane. We have something pointing flat up in the plane, and then we have something coming out, that'd be the solid wedge, and something going back into the page, that would be the dashed wedge. But all 4 attachments to that carbon in methane are all identical. So you don't have 4 unique ones, so that is not chiral. So again, just to show how this works, I'll just move this so you can see it. There we go. So you could just type chloromethane, and obviously it brings up everything else as well if you're looking for something and can't remember the name. and you can just kind of spin it around, right? You can also draw as well, so you can just add stuff to it like this, which is what we might do actually. Let's just attach a fluorine and a sulfur as well, right? And then if you just click 2D to 3D, and then just takes a little second, and there we go, right? And we get our structure. So this would be an example of a chiral compound because I've purposely made 4 completely different attachments. And we can see that if I was to, let's put the little green one at the top like that. It's often good to put hydrogen at the top if there is one. And I'm just going to spin this just like that. There we go. So this is what we had before. So if we took a mirror image, right, we would have this yellow thing kind of sitting here. The red thing would just be sitting behind it. And this green, this chlorine, would be sitting way off to the right. And then the fluorine, the light green, would still be sticking up. If we then do a 180-degree rotation, like that, until the green now is over to the right, you can see that in this case, it would not be superimposable because we would have had, don't forget, the yellow was at the front. Now we've got the red at the front, right? So it's a good way to just kind of engage with it three-dimensionally if you're struggling a little bit with doing that on paper. The other thing that I always do is, and I teach this to all of my students as well, is you can just take your thumb and your first 2 fingers and you can make that the tetrahedral structure, and then your wrist like this, or the top of your hand, my hands are kind of messed up, is pointing up. You can even put like a finger like that to represent something. And then what you can do is you can just kind of spin and rotate and then look at what you've got. If you wanted to, you could even actually write like chlorine and hydrogen and stuff on your fingers. But the idea is that we're just doing like a rotation, but you can also spin things around. So if they give it to you in a different conformation on the picture, you can kind of start with the conformation they've got, think of each thumb and finger representing something, and then rotate it to the structure that you want, or to the position that you want it in, right? It's a good way to engage with it as well. And it's an easy way to do it in the test without having to write anything. And there's nothing against spinning your hand around, right? I don't think I did it in March from memory. I don't think I really got any stereochemistry actually in that sitting, but I do remember doing that in my paper sitting back in like 2013. But that was when they asked a lot more about stereochemistry back then as well. And I remember sitting there spinning my hand around, and it worked out though. Cool. All right, and there we go. So that's really it. Oh, you can zoom it as well. I didn't even know that. There we go. That probably would have been helpful. Nice. So that's really all we need to know. 2 main skills is understanding how to identify chirality and count the number of chiral carbons, and then also testing for enantiomerism. That's really all you need. Anything beyond that, they will explain it in the STEM and you can just follow their instructions. A lot of the time it's about moving things 3-dimensionally anyway. So it's more of a visual game. It's more of like a visuospatial thinking test rather than a direct test of your understanding of stereochemistry, which is why I'm leaving that bit out. Anyway, I'll leave that there. I'd like to keep this one a little bit shorter. Leave me some feedback if you've got any for me, if there's anything else you'd like to see. This will probably be the end of the official crash course series for chemistry. There's only a little bit more to go for physics. And then I'm looking at doing one for bio, but maybe if people can comment and let me know if that's something that you would like to see, because bio is definitely not assessed all that content heavily anyway. So is that a word? So it's much more, they use the bio stuff for like experimental procedure and reasoning and problem solving, but there is a little bit in terms of genetics and maybe a little bit to do with cell structure and organelles. So for people who don't have any background in this, let me know if that's something that you'd like to see covered as well. And I can probably put together a bio series now that the chemistry is all wrapped up. Beyond that though, it doesn't mean the videos would stop. It'll mean that now what I'll do is switch to some shorter videos that pinpoint specific skills based on the actual questions that come from the ACE material. I can't actually reveal the ACE material because it's protected under copyright, but every time I make these videos, I'm going through the ACE material, all of my notes on what I found in my own sittings as well, so that it's still targeted as much as possible to the test, so it doesn't just go off down a rabbit hole of content all the way through. Otherwise, I'll leave that there. I'll quickly mention as well for people who are interested in tutoring, I have not yet been able to change my schedule. So as I mentioned, it's still early November to mid-November. My Year 12s finish around about the 10th of November, which is probably around about the time that I'll be able to kick that off. So that's still in the works. Don't worry though, I've made a list. Everyone who's contacted me in the order that people have asked, I'll get in touch with you in that order to make sure that people don't miss out. If you are interested, just let me know. I'm putting together a website so that people can sign up that way as well. But if you've already requested it, don't worry, you don't have to do that. And I'll also mention as well that there'll be 3 different offerings coming into it. So there'll be private one-on-one. There'll also be group sessions. That will probably be designed, one, for people who prefer learning in a group, because I think with GAMSAT it can have its real benefits. It'll also be a little bit more of an affordable approach as well, if you're worried about costs and things like that. And then the third one will be an essay marking system as well, based very much off of how I've done my essay feedback videos and things. So you'll get like a nice detailed run through of your essays, along with like a score band, similar to the way that ACER do it, but obviously ACER limit you to just their 2 sets of prompts. This way you can kind of just throw any prompt, get the feedback on it, get a sense of where it's at, and then as well as that, some detailed notes on writing structure, how to improve, where you've got strengths, where you've got weaknesses, and hopefully that will come in handy as well. Cool, all right, easy. I will leave that there and I will see you in the next one. Be an essay marking system as well, based very much off of how